Record time, good stuff. All right, so the next big one, big one, is called PID tuning, or PID. Okay, this stands for integral, proportional, and derivative. Okay, so you guys should know what the P, the I, and the D in this mean. Very critical vocabulary here. Okay. Proportional. Oh, okay, so what I should say is that these are parameters. P is a parameter, I is a parameter, and D is a parameter. Each of these tries to tweak our signal in slightly different ways. Okay. The way that P works, proportional, also called a proportional controller. So this is a PID controller, but you don't strictly have to have each of these three components. You can have a P controller, you can have an I controller, you can have a PI controller, you can have a PD controller. You can eliminate selectively each one of these, and I'm going to show you how to do that. But each of them does something slightly different. Okay. So again, what a proportional controller does is it tries to correct for error in a proportional way. Okay. So if this is 1 and this is 0, okay, if we are sensing, this is our input, but this is our set point. I'll just call this degrees C to make it easy. Okay, so really simple chart. This is just a temperature. This is time. Okay, between 0 and 1 degrees. So we're pretty zoomed in here, but just to give you an idea. Okay, right now, our error, delta E, defined as input minus output, right? It's the difference between what our set point is, where we want to be, and where we currently are, right? So right here, really easy, our delta E, our error, is just equal to 1 degree Celsius, which is our symbol here, right? So what the proportional controller does is it modifies the error, so delta E times P, to see how to decide its next step, how it responds to this change in set point, okay? Yeah, I'll keep that there. All right, so P, I, and D can be tuned. So what that means is that we can change P, I, and D, which is typically between 0 and 1. We can tweak those values to try to get a curve that responds just like this in the ideal case, okay? So you can plot your process, you do a set point, and then you let it go and you see what happens and you get this chart and you see where on this chart you are. Are you undershooting or underdampened? Are you overshooting or overdampened, or are you ideal? And then you tweak your P, your I, and your D accordingly to try to get as close to this ideal line as you can. And there's different effects that happen when that happens. Okay, but P in this case is whatever we want it to be. Okay, that's set by our code. Okay, so like in our structured text or in our ladder diagram, you would have a block that would be a PID block, and you would wire in 3 values to it, a P, an I, and a D. If we set P to 1, for every 1 error, it will try to correct with 1 amount of effort. You know, that might be turning your relay on or, you know, doing 1 unit of cooling. So what'll happen is that it'll correct like this. What you'll see is a slope where this is kind of like the p-value. So essentially, you can kind of think of it as the bigger your error, the harder it pushes to try to correct that, okay? That really is the P proportional controller, so the harder you push, or the bigger the error, the harder the correction. All right, I'll show you videos of all of this too to really drive it home, but I wanted to put it down on paper first. Okay. A really good example of a proportional controller and where it can go wrong is in a tilt correction situation. Okay, imagine that we have a little robot arm here that's just holding this plank upright. Okay, and this robot arm, you know, how extended it is or how retracted it is, and the verticality of this is what we're measuring here. And we try to say if we nudge this, you know, if we put a force on this, that the motor will try to correct that force back such that it's upright, right? That's our system. A proportional controller, theoretically, if I push this way with this much force, would return this way with approximately the same amount of force, okay? Or again, if I push it this way an inch, ideally it would try to correct this way by an inch, okay? However, the error for a proportional controller isn't correcting over time, okay? It's just a one shot. It's very reliant on this parameter, okay? So example, if this is supposed to be equal to 1, we never know what the ideal case is, okay? This is like us versus reality. We're trying to figure out the P, the I, and the D that is best for our system, and there can be multiple answers, okay? So we never really know what the correct answer is. We just take stabs at the dark. Assume that we want, or the the proportional value should be 1, but we don't know that. In our testing, we find that 0.98 works pretty good, right? Like for most cases, it gets us within shooting distance of where we want to be. Okay, but the issue with proportional controllers is that if they're off by a little bit, okay, because say, you know, the 0.02 here was really important, we'll always be off by 0.02. Okay, what that means for our system, in our tilt system, is if we tilt this way, our controller says we should tilt back. The end result is that it's almost tilted upright. It's off by just a little bit, but it is always and will always ever be off by that little bit because it's always responding proportional to what it's seeing. But it doesn't know, right, unless you have additional sensing on here, or rather a better controller to nudge that back into the range to account for this 0.02 error, it will always have some amount of error in it, okay? But proportional controllers are great for a lot of things. It's a very simple control system. And if you don't really care about that 0.02% of accuracy, you could call it a day, right? That might be fine enough. For the cases that it isn't, very often a PI or a proportional integral controller will. Okay, so the PID controller is like the full implementation. But very, very often in actual practice, the D is just set to 0, which means that we don't really use that part of it, okay? But we just use the P and the I, which is to say P and I are non-zero, whatever we set those values to.
What does the I stand for?
Integral. So these are mathematical concepts, by the way. If you guys have gotten to like higher level math, Calc 3, Calc 4, the integral is this integral, right? Some x dx, like the actual like integration function, and then the derivative would be the dx part. Do you guys know what a derivative is? No? Kind of? Okay. A derivative, say we have some signal that looks like this, and we want to try to find the area under this curve. Like what is this, how much area is on the whiteboard right now would be colored in green. And this was some, you know, crazy math equation. You know, something like that. you can figure out how much space is underneath here, how much area is underneath here by taking it and chopping it up into individual bars. Okay, so instead of a crazy math equation, we just have a bunch of rectangles that are next to each other. And it's really easy to figure out the area of a rectangle, right? It's just how tall is it times how wide it is. Okay, and so this technique, again, I have my angle here, has some amount of error, right? Because as I make these bars in here, there's going to be some unaccounted for space in that block, right? That technically this should be accounted for, but isn't, so my answer is going to be a little bit wrong. So the way that you make this correct, or as correct as possible to this, is you make these rectangles as small as possible, or as thin as possible. Okay, so mathematically this means that you evaluate it as the limit goes to 0, right? The width of this, it's like you calculate it and then you make it smaller. You calculate it and you make it smaller. This is the concept of a derivative. It's like the smallest slice of something you could possibly get in math, okay? In actual like digital stuff, our dx will often be one sample of something, right? So if we have a temperature sensor and we can get 1,000 samples per second, the difference between one sample and the next one would be our differential, okay? Or our derivative in this case. But sorry, that was a bit of a tangent. I just wanted you guys to know what a derivative is, which is, again, it's a vanishingly small section of it, okay? It's like if you could take the smallest bit, the smallest slice of this you possibly could, that's what it is. And if you add up all of those slices to figure out this area, that's what an integral is. Okay, it's kind of like taking the sum of your individual rectangles, adding all the area of all of those together, and you get the integral. Yeah?
So the derivative is sort of defined on a case-by-case basis, depending on what the smallest way to divide something up is?
A derivative is a mathematical concept, so it's difficult to explain. They take this concept that I'm telling you guys here, takes multiple days to explain in calc. So like, I don't want to get too into it. I'm just introducing the concept of a derivative and an integral. If you want to know more, I would wholly suggest you look it up, but I'm probably not doing it too much justice right here. In the end, you should just know that a differential or a derivative is like the difference between a reading at 1 second and the difference between the next possible reading, right? An instant later, you can think of it as, okay? And the difference between a reading at 1 instant and the difference between a reading at another instant is the difference, the differential, okay? The derivative. An integral, again, the reason that I'm telling you guys all this is an integral takes those little slices. Let me see here. Okay. So for example, if in our, sorry, the board's getting a little messy. I'm going to redraw this. So the whole reason that we have this I term is to correct the critical thing that P controllers are not great at doing, which is correcting very small errors. Okay, in our tilt scenario, if we wanted to be exactly upright, but we're ever so slightly off for our proportional controller, the proportional controller is saying, I should be here, and life is good, but we know that we have a little bit of error here. What the I allows us to do, by setting it very, very small, is it still takes the difference between these two. Again, the difference between this point and this point, okay, where we want to be and where we are, and starts adding them up, okay? So what happens is, over time, we start adding up the errors that are every instant we do a read. We go, okay, where are we at this point in time? Oh, we're still here. We add that to the total. And we get a number that goes up and up and up and up. This number is I, okay? So when we go to do a motor movement, we have the motor given to us by our P controller, right? Like the amount we need to move as demanded by our P component, most of the movement is done by the proportional controller. And now we need to add a little bit of movement from our I term, right? That's growing and growing and growing and growing. Soon enough, this I term will be sufficiently large to trigger a motor movement. It'll go click, or it'll slowly creep up. The motor will start getting more and more power fed to it as this number goes up more and more, such that it creeps smaller and smaller. Eventually, we're gonna add really small E's, right? They're gonna be like half E and quarter E. And this doesn't build up quite as fast. And in fact, we might even overshoot. Okay, so at some point, this I is gonna grow so large that the P is telling us we need to be here, but P plus I says we're all the way over here, right? We swung around back this way, okay? This is the downside of PI controllers, is that they can oscillate. Lost my eraser. All right, so worth noting here in our hysteresis example, we almost want to oscillate around our set point, right? However, oscillation is very often, more often than not really, a bad thing. For example, our tilt controller here, if we have a badly tuned P and I process on our tilt controller, when it tries to reach the center here, it'll keep bobbing back and forth. It'll go here, and then it'll go here, and then it'll go here, and then it'll go here, and here, and here, right? It'll not ever kind of settle exactly in the middle. It'll just kind of keep ticking and talking back and forth as this error tries to correct itself and overshoots, right? So what that looks like when drawn out on a more proper graph here, that this is our set point, looks like this. So we go there, and then we overshoot, and then we undershoot, and then we overshoot, and then we undershoot, and so on and so forth. Okay, so this is an oscillating system. This is also said to be an underdampened system, because ideally, it's okay if our process oscillates like this for a little while. Okay, an ideal controller, an ideal PI controller actually will oscillate a little bit, but it'll settle down. Where, you know, the first one might overshoot a lot, but the next one will overshoot less and less and less and less and less and less until it finally kind of nicely settles in there. That's what you want more often than not. We call this ringing. Ringing, when we try to reach a set point and we kind of ring around it. It just also looks like a waveform for like a ringing sound, right? This is said to be a critically dampened system, okay? Or actually, that wouldn't be really, that's not ideal. Critically dampened is if it would like, you know, really nicely sidled up like that. You could call this well-tuned, really. So what this might look like for our tilt situation, okay, is if we start off and we're tilted this far, because that's just where we happen to start the system, right? It'll probably want to try to overcorrect really hard because the proportional controller is going like, whoa, there's so much error here. We got to shove back really hard. I is probably pretty high too. So it shoves back this way, but then it overshoots. So now it's here, and now it has to go back a little bit less and a little bit less, and it'll kind of like clock back and forth until it sidles up nice and straight, ideally, right, in our well-tuned system. Okay. There are really advanced ways to figure out what P and what I are in order to get these parameters, but sometimes you really just have to test it. Okay, there are algorithmic ways that you can like run simulations and have the microcontroller like figure out what it's doing and tweak itself. But more often than not, you just have to kind of like pick a P, you know, call it like 0.5 and then tune that, and then pick an I and see how that works, and then raise I or raise P or lower P. Okay, so tuning a system, that's why they really call it PID tuning, is you sitting down with the thing that you're controlling and tweaking these parameters until it starts to work well. It sounds like not right, but that is very often what happens. So again, these are numbers. The thing that we wire up, eventually we will have a function block within our ladder diagram or within our function block diagram that will take a process in, probably our set point, or no, that would be like on off, and it would probably take like a set point variable, and it would probably take like a P, an I, and a D that you would wire in as variables. And then you would probably, again, have like an output block that would lead to your coil that would turn on and off your relay that would be controlling this thing. So lots of cases, our output can either be on or off, right? Our heater's on, our heater's off, or we could kind of have more gradual output where we could control how much current is going into our heater, for example, or control how hard our motor is pushing back against this arm to try to right it. Not necessarily all on or all off. So what this really does more often than not is control the duty cycle. Okay, duty cycle. This is what a 50% duty cycle looks like. This is what a 25% duty cycle looks like. This is what a 100% duty cycle looks like. Okay, can imagine that this waveform is on 50% of the time and off the other 50% of the time. And then this repeats itself like 1,000 times a second. Okay, so every 1,000th of a second, it's on for half of a 1,000th and then off for the second half of the 1,000th. Over here, it's on 25% of the time and off 100% of the time. Okay, so on and so forth. When we add these together and give the timing, how long our relay should be on versus how long it should be off, that's what our PI processes are giving us. They're not giving us like motor positions or motor force. It's saying how long it should be on and how long it should be off. Okay. Very often what happens is that the output of our controller here, I'm just going to start over. Do you guys have this down in notes? I'm going to erase it. Okay. I need a blank slate. I'm like finding small spots to write in. So make sure you guys know like the different damping, underdamping, overdamping. Make sure you know what P does, what I does, and I'll tell you D in a second. That one's just not as used as often, so I'm leaving it for last. But the P and I definitely are good to know how to work those. I guess I'll go over that now. So the D really works much more like the derivative, like I said before, or like the proportional works before, okay? Where the difference between our set point, for example, if this is our set point, and if this was our current, then this would be our delta E, right? So if we take a portion of that delta E and added it to our D value, it's literally like at each point in time, what is that value? And then add the error to it. Okay, so before our output, again, it was like motor force or motor position would be the P math plus the I math. Again, what this actually looks like is the P is Y = mx plus b. All right, the P is the mx part, okay? So in our math, the output is equal to m times x, where m is P for proportional, plus the integral, which again looks like this, which is the sum of the error that we had before. You guys aren't going to do any of this math. Again, I just want you to know the concept. Okay, the sum of those plus d plus the, I guess it would be d times delta E. Okay, so this would be like what the math is literally doing if we were to run it through the calculator on what is the PID algorithm. It's this math. It's the proportional component, which is y equals mx plus b, right? Our slope, our corrective slope, our proportional slope. It's our integral component, right? How much error has there accumulated over time, summing all of that up. Okay, so this term will grow over time or shrink over time. And what is the current difference between the error and where we are now? Okay, so the D is great at like small corrections. It's like instantaneous corrections. The thing that I can't do is respond quickly because it sums over time, right? It grows and it shrinks. It's rather slow depending on the error. But D responds accordingly. If we had, for whatever instance, we had a line like this and super suddenly, wow, we're off the charts. An integral, a PI controller, would not fare very well against this sudden change, okay? It might, kind of go like this in response, huge long curve, and our process variable might, never recover because we don't respond to it quick enough. That's where the D controller comes in. The D controller at any minute looks at how much error is there at this specific second. So if we get this large amount of error right here, it'll go, whoa, there's a huge error, let's correct that. And now our set point might kind of only be around here, might not be as disastrous, right? However, if you get the wrong parameter for D or for I or for P, they'll dominate your math and you'll have no chance of tuning the circuit, right? So that's why it can be really tricky to tune these things, because if your D is really far off and your P and I are well tuned, you might be where you would want to be normally, but it has you rocketing off over here because it's just has too much strength. It's correcting too hard, okay? So that's the math behind the P, the I, and the D. And the D is literally the error. It's kind of like at each instant, I'm going to try to fight that error. And the D, the parameter, is how hard it tries to fight. Okay, it's D times the error, right? So if D is really hard, it'll, at an instantaneous error, it'll try really hard to correct. Or if D is really small, it'll kind of try not that hard. It'll see the difference and it'll try to correct it, but the overall performance might be dominated by like your P and I variables, okay? Any questions? No? Okay. So again, you're never, ever, probably ever going to have to deal with this. Okay, this is engineer stuff, right? Computer science people will have to program a function that does this probably at some point. But for all of you guys, this is what they made function block diagrams and ladder diagrams for. It's because you just have a block that we drag into our canvas that says PID controller. And then we just have to do the P, the I, and the D and figure out what those values should be. Okay. Sorry?
There's something else for N. There's PID, and there's something else. On-off switch, there's a coil.
Yeah, so your block has inputs and outputs, right? So I don't actually know what the inputs are. I'd have to double check, but there most surely is like an input coil, or sorry, an input contact and an output coil. This would be your controlling, right? This is your relay, this is your heater, it's whatever. And then this would be your P, this is your I, this is your D.
There's something above P this is on that. I have.
It's the contact, no?
Not the switch. Some other input, I think.
Oh, maybe our sensor input. Right, we'll probably have another input here that's our temperature sensor. That's probably there. I don't think I had that before, but that's probably more like what it will actually be. Okay, so again, that's all of the vocab. That's all the concepts down on paper. Now we're just going to go over it again, make sure you guys understand it, get some more video, some more context with it, and then we'll kind of explain the different parts of the upcoming lab as well. So while this is going down, so the whole reason that we have this other simulator board is to do things just like this, to test PID or just like naive control systems. It provides a platform that we can test control systems on. There's two banks of resistors on here, individually controllable, right? So if we turn one resistor bank on, we get one amount of heat flowing into the system, and if we turn both on, we get a lot of heat going into the system. So that way you can kind of do it like, do we want to quickly reach our set point by turning two heaters on, and then turn one off as it starts to approach, or whatever. There's lots of different flexible ways to do this, as well as a temperature sensor on here. So we can close that loop where we have that feedback, that input on what is the current temperature of this board. Do we want to try to keep that within some limit, some set point, and all of that. So that's what we're going to be doing in the lab just soon enough. Keep that in mind as we're applying these concepts.
Brought to you by us, ELT140. Join the top 1% of PLC programmers. Learn from the world's best so you can join their rank. Head on over to realparts.com and start learning now. In this video, we're going to talk about the PID controller and its transformation from a single station device to what it has evolved into today. We're going to explain why PID controllers are used in industrial processes instead of simple on-off controllers. We'll illustrate how controller settings called proportional, integral, and derivative affect different processes under control. We'll also provide an overview of the very important activity called controller tuning. Let's start with a discussion about home temperature control, as it's familiar to lots of people. This house has a furnace that distributes heat throughout, and a wall-mounted controller called a thermostat. The thermostat has a sensor that measures the house temperature and compares that measurement to an adjustable set point. If the room temperature is below the set point, the furnace is turned on. When the room temperature increases above the set point, the furnace turns off. This type of control is referred to as on-off or bang-bang control. Here's a plot of what the room temperature does over a period of time as the furnace turns on and off. As you can see, the temperature is not exactly held at the set point of 70 degrees Fahrenheit, but cycles above and below the set point. On-off control may be okay for your house, but it is not okay for industrial processes or motion control. Let's look at an example of tank level control to explain why. The valve fills the tank as the pump drains it. If the valve is operated with on-off control, the water will fluctuate around the 50% set point. For our purpose, let's say the fluctuation is plus or minus 10%. In most industrial applications, this fluctuation around the set point is not acceptable. Okay, well, what if it's possible to throttle the valve and place it in any position between on and off? Now we can move on to talking about a PID controller. P stands for proportional, I stands for integral, and D stands for derivative. Because every process responds differently, the PID controller determines how much and how quickly correction is applied by using varying amounts of proportional, integral, and derivative action. Each block contributes a unique signal that is added together to create the controller output signal. Let's look at how a PID controller fits into a feedback control loop. The controller is responsible for ensuring that the process remains as close to the desired value as possible, regardless of various disruptions. The controller compares the transmitter process variable, or PV signal, and the set point. Based on that comparison, the controller produces an output signal to operate the final control element. This PID controller output is capable of operating the final control element over its entire 100% range. Most modern PID controllers are part of a PLC or DCS and are created in the program control logic using block commands. Before PLCs came along, a PID controller was a standalone device, responsible for controlling one loop. A control room would have dozens or hundreds of standalone controllers mounted on a panel. There are still